welcome. So, in today's lecture we are going to discuss chemical reaction equilibrium. So, basically we are looking at the statistical thermodynamics or the molecular thermodynamics of an ideal gas mixture where the components can undergo chemical reaction with each other. Now, in this particular reactive mixture of ideal gases, we are going to focus our attention on a homogeneous gas phase chemical reaction that is typically something like this. So, you obviously know that famous reaction between hydrogen and nitrogen giving rise to ammonia. So, if I take 3 moles of hydrogen, react it with 1 mole of nitrogen, I get 2 moles of ammonia. So, in this way I am writing A1 capital A1 plus A2 capital A2 giving rise to some A3 capital A3. Okay. So, what is my A1, the reactant A1? If I compare it with this example, my reactant A1 is this hydrogen molecule. So, what is this stoichiometric coefficient small a1? In this example, that is equal to 3. Similarly, I can identify A2 with my reactant nitrogen, and the corresponding stoichiometric coefficient that I see in this equation is A2 equal to 1. Similarly, you see that A3 can be denoted in terms of the ammonia, which is the product of the reaction, and the stoichiometric coefficient that appears in this balanced chemical equation that gives me A3 equal to 2. Whatever I am going to discuss here, for the sake of simplicity, I am going to stick to this particular type of chemical reaction, although any number of reactants giving rise to any number of products can be handled, but once again for the sake of simplicity, I am going to keep myself focused on 2 reactants and 1 product for which the stoichiometrically balanced chemical equation is known, and in that Ai, if it is either a reactant or a product, the stoichiometric coefficient in the balanced chemical equation is small ai. With this background in mind, I also would like to write down rather artificially this equation. So, it is as if I replaced the reversibility sign here by an equality sign, taken these 2 terms on the right hand side, and this is the equation that we get. So, this basically tells me that any general chemical reaction can be written in the form of an algebraic equation, which says that AIs are the participants, or any participant in the reaction, the ith participant in the reaction, and nu I is the stoichiometric coefficient of the ith participant in the balanced chemical reaction, which is this. And therefore, as you understand, nu I is equal to plus ai if this ith component is a product, and it is equal to minus ai if this ith participant or ith component of the reactive mixture is a reactant. We will keep this in mind and then try and see that with this description we are going to have in mind the well known result in gas phase reaction, and especially in chemical reaction equilibrium, that is the law of mass action. So, what is the law of mass action? If you have a chemical reaction which has attained equilibrium, it has been shown using a large body of experimental data that you can always define a constant in terms of the concentration, mass density or number density of each of the components present in the reaction mixture raised to the power of the corresponding stoichiometric coefficient in the balanced chemical equation. And therefore, for this particular chemical reaction, we see that this is going to be rho 3, which is the product raised to the power of A3, because for the reactant my nu 3 is equal to plus A3, but for the reactants, this is for the products, for the reactants nu 1 is going to be minus A1, and therefore, it comes to the denominator when I take away the sign. So, basically the law of mass action says that this reaction, when it starts, there is initially A1 and A2, and if you allow the reaction to proceed, it would start producing A3, and eventually a situation would be reached when I would say that an equilibrium has been reached. The reaction does not seem to proceed either in the forward or the backward direction, and a constant ratio of these numbers are being maintained, which is known as the equilibrium constant. So, we are going to look at the reactive mixture of an ideal gas and try to understand why at all something like an equilibrium constant should exist in a simple case as shown here. The next thing that I would like to mention over here, that in an ideal gas system, if you have a homogeneous gas phase reaction and individually this gas mixture of A1, A2 and A3 is behaving like an ideal gas mixture at equilibrium, it depends on temperature and temperature only, which means this constant value at a given temperature, this equilibrium constant is a constant value at a given temperature. Now, if for the same reaction you change the temperature, then you will find that the system will establish equilibrium such that this K equilibrium value is another constant depending on what your new temperature is. So, once again we ask this question, why is it so that K equilibrium, if it exists, is a function of temperature only? For example, it does not depend on the pressure of the gas. And finally, there is something called the Chatelier principle that you must have encountered while studying the chemical equilibrium, thermodynamics and chemical equilibrium. So, what is the Chatelier principle? It says that if a system at equilibrium is disturbed by a change in a factor like a temperature or pressure or concentration of one of the components, then the system will shift its equilibrium position so as to counteract the effect of the disturbance. So, basically when the system is in chemical equilibrium, then you impose certain change in the system so that this equilibrium is disturbed. So, basically what you have created is a stress, and the system responds to the stress such that it still goes back to an equilibrium, but it goes back to an equilibrium in such a way that it counteracts the stress or nullifies the effect of this external perturbation. So, in this particular lecture, what we will be interested in is if I change the equilibrium temperature, then what will be the effect on K equilibrium? I said K equilibrium is a function of temperature. Therefore, I can very easily find out what happens to del K equilibrium del T. Actually, what we will be looking at is del ln K del T, this particular factor, as you will see from the next discussion. So, with this goal in mind, I have to establish that something like a law of mass action can be justified. The equilibrium constant for a homogeneous gas phase reaction is independent of pressure, but it depends on temperature. And finally, I would like to understand the behavior of K as a function of T such that I can justify the observation that led to formulation of the Le Chatelier principle. Now, once again I am going to use the formalism of canonical ensemble for this simple chemical reaction, and I am going to study this under a condition of constant temperature, constant pressure, that is the usual condition. But in this case, I am going to assume certain things so that I am able to use the formalism of canonical ensemble. So, the first assumption is that the mixture of the reactant and the product gases has already attained the chemical equilibrium at a given temperature in a closed vessel. So, even if the individual number of particles are changing could change because of chemical reaction, what we observe is an apparent chemical equilibrium mixture which is at standstill. Okay. Now, what we will say that obviously then in this equilibrated mixture, the number of particles of the component Ai is given by Ni, and with time Ni remains constant. That is our experimental observation. Now, what is it that I have in my reaction mixture? At equilibrium, I have some N1 particles of the reactant A1, I have some N2 particles of reactant A2, and in equilibrium with them I have some N3 particles of the product A3. And therefore, very easily I can write down that the canonical partition function for a mixture like this is written in terms of the individual single particle partition functions of the component 1, component 2 and component 3. Now, by definition we know that mu is equal to minus kBt del ln capital Q del Ni, keeping T, V and all Nj's not equal to I constant, and this gives me mu I, or the chemical potential of the ith component in the equilibrium mixture. Now, I have been able to show that for this particular system, my capital Q is nothing but Q1 to the power of N1 divided by N1 factorial into Q2 to the power of N2 divided by N2 factorial into Q3 to the power of N3 divided by N3 factorial. Okay. So, what is ln Q? Ln capital Q, that is going to be nothing but ln of each of these terms, right, N1 divided by N1 factorial plus ln of Q2 to the power of N2 by N2 factorial, and the last term that depends on N3. So, Q3 to the power of N3 divided by N3 factorial, right. Now, let me try to find out mu 1. Okay. So, in that case I will have to find out this derivative del ln Q del N1, keeping temperature, volume, N2 and N3 constant. So, for this purpose I will have to focus on this quantity only, because the rest will remain constant under this given condition of taking the derivative. So, now let me focus on what ln Q is for very large number of N1. So, I can write this as N1 ln Q1 minus N1 ln N1 plus N1 using Stirling approximation, and plus terms which will remain constant under the constant condition of constant temperature, volume, constant N2 and N3. So, what is del ln Q del N1? Keeping T, V and N2 and N3 constant, that gives me that I must be having ln Q1 minus ln N1 minus N1 into 1 by N1 plus 1. Okay. Now, these two terms cancel with each other. So, what I am left with is del ln Q del N1 under the condition of constant temperature, volume, N2 and N3, that is equal to ln Q1 by N1, right. So, going back, since I know that mu 1 will be given by this relationship, I can very easily write that mu 1 would be equal to minus kBt del ln Q del N1, keeping temperature, volume, N2 and N3 constant. So, in general I should be able to write that mu I, the ith species present in the reaction mixture is minus kBt ln Qi by Ni. Now, what is the consequence of this formulation? If we go back and see that when the chemical reaction has achieved an equilibrium and I then do something to perturb this system slightly, then the system will still remain in equilibrium. Now, this perturbation can be induced in the system by making the system proceed in a forward direction by a only very small amount, say dψ amount. So, let us say that dψ is the extent of reaction. Now, here this will result in a change in the number of particles of each species present in the medium as dNi equal to nu I into dψ, and that is because of the existence of this stoichiometrically balanced chemical equation for the chemical reaction. So, that basically tells me that I can rewrite dF as this. Now, by the design of my experiment, dψ is not equal to 0. Therefore, if the system still attains equilibrium, in that case I would say that even if I allow the system to move forward in one direction infinitesimally, and if the system still retains equilibrium, I must be having this condition that under constant temperature and the constant volume condition dFdV must be equal to 0, but dFdV is given by this. As a result, I would say that the equilibrium condition for this chemical reaction mixture is that I look at the stoichiometric coefficients in the balanced chemical equation for each component in the reaction mixture, multiply it with the corresponding chemical potential, and then I sum over all such components present in the reaction mixture. Then at equilibrium, for the equilibrium composition of the system, this quantity, this summation is going to be equal to 0. So, now we understand that at equilibrium, when a relationship like this is valid, then for this particular expression, for this particular chemical reaction equilibrium, we can very easily write that A3 mu 3 minus A1 mu 1 minus A2 mu 2 must be equal to 0. Now, we have already shown that each of the individual mu's are related to minus kT ln Qi by Ni. So, now let us write this particular expression that is given over here in terms of the individual mu's. Okay. So, what I must be having is A3 then mu 3. So, what is mu 3? That is minus kBt ln Q3 by N3. Then I have minus A1 into the same expression that I have for mu 1 being put in here. So, this is given by this, then minus A2 into minus kBt ln the contribution coming from Q2 and N2, and therefore, at equilibrium I must be having this quantity equal to 0. Now, I simplify many of these things as I see that this kT terms can be easily dropped because on this side I have 0. So, what I find is that I must be having ln Q3 to the power of A3 divided by N3 to the power of A3, then minus ln Q1 to the power of A1 divided by N1 to the power of A1 minus ln Q2 to the power of A2 divided by N2 to the power of A2, that must be equal to 0. Okay. Now, I collect all these logarithmic terms. So, what I get is I must be having ln Q3 to the power of A3 divided by N3 to the power of, okay, maybe I will write down the Q terms together. So, divided by q1 to the power of a1 into q2 to the power of a2 into n1 to the power of a1 into n2 to the power of a2 divided by n3 to the power of a3. This entire thing must be equal to 0. Logarithm of this quantity is equal to 0. So, basically I must be able to say that whatever appears within this bracket must be equal to 1. As a result, now we can write directly that q1 to the power of a1 by into q2 to the power of a2 divided by q3 to the power of a3, that is equal to n3 to the power of n1 to the power of a1, n2 to the power of a2 divided by n3 to the power of a3. Okay. As you see that this ratio is already related to the number of particles present in the equilibrated reaction mixture under the given condition of constant temperature and volume. So, what I am going to do is I am going to look at what happens to this term n3 to the power of a3 divided by n1 to the power of a1 and n2 to the power of a2. So, this is given by at equilibrium this relationship. Okay. So, that is going to be given by q3 to the power of a3 divided by q1 to the power of a1 into q2 to the power of a2. Clear? Now, I divide each side, each of these quantities by V. So, what I have here is n3 by V to the power of a3. Similarly, instead of n1, I replace it with this quantity. Instead of n2, I replace it with n2 by V, where V is the total volume of the system. So, what do I have on the right hand side? I have q3 by V to the power of a3 divided by q1 by V to the power of a1 into q2 by V to the power of a2. So, now as you see that we have been able to formulate the left hand side in terms of the number density of the components present in the chemical equilibrium mixture. So, this quantity is nothing but rho 3 to the power of a3 and this quantity is nothing but rho 1 to the power of a3 and this is rho 2 to the power of a3. So, now I find that if I look very closely at the ratio that I have formed, what I have is in the numerator I have the number density of the product or the concentration of the product raised to the power of the stoichiometric coefficient present in its balanced chemical equation divided by concentration of the reactants, each raised respectively to the power by the stoichiometric coefficient appearing in the balanced chemical equation. So, let me call this ratio as something like K. Now, at equilibrium this K is given by this. So, now let us have a look at what happens to this ratio defined as K. So, now I find that in this particular case capital K is given by q3 by V to the power of a3 divided by the same quantity written corresponding to the reactants. Now, each of the reactants and the products, they are ideal gases. Therefore, I can write down that Qy is going to be something like V divided by say lambda I cubed multiplied by Q internal, right. So, what is Qi by V? Qi by V this quantity is nothing but Q internal divided by lambda I cubed. Now, look at the nature of what I have on the right hand side. This part depends on the chemical nature of the component I, and this depends not only on the mass Mi of the ith component in the reaction mixture, but it also depends on temperature. And therefore, I would say that this Qi in this reaction mixture is a function of temperature for a given combination of reactants and products. Therefore, if I go back, I see that K, this ratio at a given temperature, is some complicated function of temperature and temperature only. There is no dependence on pressure or any other external parameter. So, that is exactly what we have shown here, and then we conclude that yes, at a given temperature, Qi by V for every component I in the chemical reaction mixture is a function of temperature only. As a result, I would say that at a given temperature, this ratio of concentrations, each raised to the power of the stoichiometric coefficient in the balanced chemical equation, is a constant, and this constant is a function of temperature and temperature only. So, the last portion that we need to discuss over here is that, so in general, for a given chemical reaction that is represented like this, I can write down the K equilibrium as a function of temperature, and in terms of the individual components of the equilibrium mixture, this is given by a product of several terms, and here I runs over all the reactants and the products present in the equilibrated mixture, reaction mixture, and small qi is the single particle partition function for the ith component, and nu I is the associated stoichiometric coefficient as given by this balanced chemical equation. Now, with this background in mind, you can now ask the question, what happens if I change the temperature of the system? K equilibrium is a function of temperature. So, how will this quantity change as I change the temperature? So, for this purpose, what we do is we just try and take a logarithm of this K. So, logarithm of K is given by this expression, which is fairly simple, and then I try to find out what is d ln k dt. How does the logarithm of this equilibrium constant vary as a function of temperature? Now, as you see that this will be given by the nu I, which is fixed for a given chemical reaction, that remains unchanged. So, now what I have is, I have this temperature derivative of ln small q I under conditions of V, constant V and constant number of particles. Now, as you would remember from the formalism, that the average energy E or the internal energy is in general given in terms of the ln q derivative with respect to temperature as del ln q del T, keeping constant volume and number of particles. Now, here what we have is something very similar. As you see that this is something which corresponds to some energy powered molecule of type I, because small q I is the single particle partition function, and therefore, I can very easily write this expression as d ln k dt is equal to nu I into E I by k B T square. Now, what is this quantity? So, for the given chemical reaction, if I write down explicitly what d ln k dt is turning out to be, I have here first for I equal to 3, that is nu 3, then E 3 by kBt square, then plus nu1 E1 by kBt square plus nu2 into E2 by kBt square. Now, I simplify this, I take 1 by kBt square outside, and for this equation I put in the respective values of the stoichiometric coefficients. So, this is A3 E3 minus A1 E1 minus A2 E2. So, what is it that I have here? What I have is, this is the internal energy per molecule of the reactant. This is multiplied by the stoichiometric coefficient appearing in the balanced chemical reaction minus the same terms appearing for the reactants. And therefore, I can say that for this reaction where A1 moles of capital A1 reacted with small a2 moles of capital A2 giving rise to small a3 moles of capital A3, then what is the change in reaction energy? Let me call it delta U naught. Then I find that this must be A3 E3 minus A1 E1 plus A1 E2, A2 E2. So, this is the total internal energy per molecule present after the reaction, and this is the total internal energy present before the reaction. So, this is nothing but the change in internal energy because of the reaction, and therefore, I can very easily write that dln k dt, that is equal to delta U naught by kBt square, right. If I do this entire exercise for per mole of the species, then dln k dt will be related to delta U per mole divided by capital R T square. So, now we have got this very important result that dln k dt is equal to delta U naught by kt square, which can eventually be written in terms of the per mole quantities. Now, as I understand that I can have two different types of chemical reactions. Type 1 where delta U naught, that is the energy content change as the system goes from the reactant to the product state is less than 0, or basically I am talking about exothermic reactions, right, or it may so happen that delta U naught is greater than 0. In that case, I am talking about endothermic reactions. Okay. So, what I understand is that if I have an exothermic reaction, then dln k dt is less than 0. Therefore, the equilibrium constant will decrease if I increase the temperature. This means that when the reaction proceeds with release of heat, increase in temperature actually pushes the equilibrium towards the reactant side. Similarly, for delta U naught greater than 0, I have dln k dt greater than 0, and therefore, in this case we will have with increase in temperature an increased value of k, which will shift the equilibrium to more towards the product side, and that is exactly what is the content of the La Chatelier principle. So, what we have achieved over here is that we have achieved a molecular definition of the equilibrium constant k, and we find that depending on the chemical nature of what A1, A2 or A3 is, in this example we could have actually found out the Qi by V's and therefore connect the molecular properties to the overall equilibrium constant. So, this is an application that we are going to take up in the assignment portion for this lecture, where we will be able to see that how the underlying molecular structure actually controls the equilibrium constant or the overall yield of a given chemical reaction. So, that makes a molecular interpretation for getting higher yield or lower yield in a chemical reaction much more quantitative. Thank you.